now this brings us to learning the concept of Newton's third law. And believe it or not, this is the most unintuitive law out of all the three laws. And that's saying a lot. If you remember, the first law and the second law basically says that if for ages and ages, which is very, very natural that people think that force is required for motion to happen, right? Because nowadays we can easily, I've never been to space, but I suspect neither have you, but it's still, we've watched enough movies and sort of get enough sort of sense in the modern age that if things are in space free from any forces, they will continue moving, right? But back in the day, this is extremely counterintuitive. The first law and the second law that says that because the quickest thing that first of all, everything's bound to Earth, right? And sort of the quickest thing they don't sort of have speeding trains and etc. like that, is maybe a horse dragging a carriage. And every sane person in the world would think that, well, you need horsepower, right? That's where the words come from. You need horses, you need some sort of force to drag things for motion to happen. If you don't have a force, things will naturally come to a stop. This is, even back in the Greek philosophers, this is their theory of motion, which Newton completely revolutionized, and now we have a very much better understanding and a much more correct understanding of how the world works and how motion works. Is it does not require any force for it to maintain motion. If something is in motion, it will go on forever, and force is needed counterintuitively. It's needed to stop it, right? It will keep, otherwise it keeps on going forever, right? Okay, so now hopefully by now this becomes a very natural fact for you, but this is probably what students still struggle with. What this says is every force, you've probably heard this in qualitative way, but very few students actually am able to internalize it and absorb what it really means. And that's what I want you to try to do. Of course, the statement says, you may have read this in the textbook already, if you apply any force on something else, you'll receive an equal and opposite force. So let me put it in slightly more rigorous form. So if A exerts a force on B, then B exerts an equal amount of force and an equal amount of force in the opposite direction. On A. Okay, so this is sometimes known as the equal and opposite force, right? So the sort of reaction from B, if A pushes on B, it is a very democratic world that they will actually exert back an equal amount of force onto you. You have no gain, no lose. All right. So as you can see, as I always say, mathematicians and physicists are the laziest people you'll meet. So having to write this is a huge pain. So let's write it in an easier way with math. How I can do that is just this. Using vectors. And I can put this in a box. Notice how much easier it is to write this. All right, so let's understand this first, right? Remember, a vector is an arrow. So I'm saying that if this is the force on A by B is going, let's say, this way, then the force on B by A would be the same arrow, right? Notice that if I look at the magnitude on both sides, they will be the same. But if I put a negative sign, right? If I do not have a negative sign, they will be pointing the same way. One of them like this, and other BA, right? And I'm saying one is the negative or other, and you've learned from since day one in lecture one, right? How does arrows work, or how does vectors work? If I put a minus sign, you just simply change the direction of the arrow. So you have equal length and opposite direction. Okay. Now, quick comment. Got a lot of get usually a lot of questions about notation. Does this mean the force on A by B, or is it the force by A on B? Is it on A by B or by A on B? Or which way does the grammar work? I can never remember it, to be honest. So here it doesn't really matter where I put the minus sign, it's the same. But when it matters, what I usually write is I actually write it explicitly. As you saw in the question earlier, I write on the car by the truck. Right? If I have box A and box B, I'll write on A by B, right? Because grammatically, probably both ways work. The force by B on A, force on A by B. I can never remember which way is which. If you have a good way of remembering it, that's good. I try to write it once like this. Now, of course, we're lazy, right? So I wouldn't want to keep writing my subscripts and fine prints over and over again in equations, especially if I have 5 steps. I don't want to keep reproducing this. So I will write this once in the diagram and then I'll give it a name. So let's say this is a problem where this is box A and it's being pushed by box B. We'll see something like this later on. So the contact force is here, then I'll have force A by B, right? So what I will do is I will label that there and then I'll give it a name. Maybe just F if it's not confusing with anything else. Right? If it is confusing with something else, I'll probably invent another thing, maybe P, the push, right? Like that. So I'll give it a name and then I'll be able to use it. And then later on, if there's another push over here, I'll call it P prime or P1, P2, whatever. But I have defined it somewhere, and then I can keep using it. Okay, so this is the general strategy. All mathematicians do this. That's the good way. That's a good practice to do it. In my mind, it's even clearer than you use a. But if you use the convention correctly, follow the textbook. That's also fine. If you know what you're doing, that's fine. I never know what I'm doing with these which way it goes. All right. So a quick comment over there. Another thing is to really understand this, right? Is to break this up, which says the magnitude is the same. Okay, so this is another way to write it like this. And so the magnitude, remember, no vector sign on top is the magnitude. Okay, magnitude is the same, but the direction, there's no symbol for direction. So we just say direction is opposite. Okay, so this is sort of taking into both statements, the equal force and opposite direction, equal amount and opposite direction, and summarizing it in one equation over here. Okay, now to really understand this, right, that we immediately have an immediate answer to the 2 thinking questions we have, right? The question 1, when I had the truck and the car, okay, look how they get simpler and simpler as I keep drawing them. Then this is the force on the car by truck. It's the same amount. They're opposite direction for sure. That's the easy part, right? Anyone can tell you that. But it's same as the force on the truck by the car. Okay, see how it gets lazier? If you know what I'm talking about, that's fine. But in practice, in your real work, it's best to write it out once and then give it a name and use that name later on. Okay, you'll see me doing proper examples more as well. Okay, so the answer is it's the same. The same thing for the second. This is extremely counterintuitive, right? The force, I almost misleadingly draw that as a longer arrow. Sorry, I think I drew that as a longer arrow to mislead you. So do blame me on that. That the Earth is more massive, so it looks like it pulls the moon more. However, that's not true. We'll see this specific case a little bit later in a few lectures time, but it is exactly the same amount of force. All right, it's just in the opposite direction. All right, how do you know this is true? This is probably the hardest bit, right? It's so counterintuitive. Then how do we know it's true? So in other words, I should ask myself, what is a law? I've used this word a couple of times already. Newton's first law, second law, third law. And throughout physics, you will go on and learn more laws like Ohm's law, Maxwell's law, and Faraday's law, other laws in 3B and then 3C as well, Hooke's law, something like that. What is a law? Well, a law is nothing more than an observation that is tested. So Newton realized that if I state things in these three laws, or for example this one, and if I can keep testing it and if it's true, then it looks like it's true for most cases. I'm going to write this as like a general principle. Now, is there an explanation of the law? A lot of times the answer is no, especially at the time that it is conceived. When Newton was conceiving this law, he does not know why this is true. So I cannot provide you with an explanation of why this is true. He wrote down F equals ma, so he realized that forces change acceleration. But if you ask him why, he cannot tell you. It's an observational fact. Now, does that mean that it does not have a reason why? Not necessary, because as we keep doing research, this is what physics, cutting edge physics research is about, to try to understand, keep asking why, right? And we do understand nowadays, we do actually understand why this is true. However, it's actually a very, very deep reason. And I would say the most correct reasoning was only developed in the past 70 years. For ages, if you were born 70 years ago, earlier, I would have to tell you there is no reason. I cannot properly explain why this is true. Okay, you can answer that by, they will give you an answer that, oh, it's from the conservation of momentum, which we'll learn. But why is momentum conserved? Then it realized it's to do with the symmetry of the world, which is something very deep, right? So it's something that we only recently know why. But at the time it is conceived, and the law of law is basically, it's an observational fact. And sometimes when I used to teach physics, I've got an interesting comment. Someone asked me when I was a tutor, and students asked, hey, you do research in physics, right? What is there to research? I thought everything was figured out like 300 years ago. So especially for theoretical physics, there's lots, first of all, experimentally, there's still a lot to discover about how things work. But for theoretical physics, we basically keep asking why and see if we can find a reason or understand truly why these things happen. Anyway, so that's what a law is. Also, if you keep asking why, and this is a good thing, by the way, in general, physics is about studying why things happen, right? So you should always ask why. However, there must always be a starting point to logic. Otherwise, you go in circles. Like, why is the ocean blue? Well, because the ocean reflects the light from the sky, and the sky is blue, so the ocean is blue. Then you ask, well, why is the sky blue? Well, because the ocean is blue. Well, then you go in circles. So at some point, you need a starting point. And laws are usually the starting point. So the inventor of laws are basically stating a starting point of the theory. So let's say, okay, this may be counterintuitive, but please accept this. All right, suspend your disbelief, accept this. If you accept it, if you believe this is true, then I can explain everything else. Okay, that's why some people say science is like religion. I won't comment on that, but the other perspective of looking at this is, I've observed this enough times that this seems to follow a pattern. Even though I don't know why this is true, if I accept this is true, then I can explain everything else. All right, so Newton basically created these three laws, and he can explain almost every motion on Earth. All right, so we're going to look at some of the motions in the next couple of videos.